All right, so very quickly, we're gonna pick up where we left off on Friday. So we're gonna start from this slide. This is give you the structure between hemoglobin and myoglobin. And myoglobin is the monomer. And then the hemoglobin is the tetramer. Okay, so for hemoglobin, you can think of it as essentially 4 myoglobin associated together. We have myoglobin as a monomeric protein and hemoglobin as heterotetramer, meaning that if it's a heteromer, whatever mer, indicating that it has 2 different subunits. In this case, you have 2 alpha, 2 beta. And again, we see that in hemoglobin and myoglobin, both of them, these are composed of primarily alpha helical domains. Okay, so primarily alpha helices. And most importantly, inside of the myoglobin and hemoglobin have a prosthetic group. That's very, very important. And for every monomer, really, or every subunit, okay, you will have one of these prosthetic group. And this particular prosthetic group is composed of a heme. And then inside the heme, you have an iron ion. Now, again, prosthetic groups are cofactor molecules that are tightly bound to a protein. And these prosthetic groups are usually important for the function of the protein. In this case, for hemoglobin and myoglobin, the heme is important for carrying molecular oxygen. Now, for some enzymes, you will see enzymes later on. You will see that for enzymes, they could be involved in catalysis. They could be involved in all sorts of different functions. Heme is a large molecule. It's composed of 2 things primarily. One is a porphyrin ring, and porphyrin ring is essentially a large aromatic compound that has a lot of these double bond structures, so it's conjugated. And then for heme, for porphyrin, you also got these 4 nitrogens essentially there so that you can coordinate a metal atom here via interactions. Right? Now, so if you have porphyrin and you give it a iron molecule, and in this case it has to be iron 2+, you'll see how that's important. And in this case, if you have iron 2+ atom inside of the cell, then what this enzyme will do is it will grab it and then put it in the middle of the heme. Similar to hemes, you have things like chlorophyll. Chlorophyll, pretty much you have the same general macro cycle structure. And instead of having a iron inside, in chlorophyll you have a magnesium ion. Okay, and then that will give it a different color. Okay, so this is something that you see a lot in biology. All right, so coming back to this slide, here's to show you how the iron atom is coordinated inside the heme. Okay, and this is actually quite important. So you guys know that anything aromatic is in general a plane. Okay, it's planar. Why? Because it has that pi orbital that can sort of, share the electrons across the entire molecule. Right? So these things are planar. So then if you have a atom, metal atom inside of this plane, okay, you will have, let's say, iron atom right here, and surrounding it is the heme. And heme is the plane that captures the iron atom along the horizontal positions. So essentially your iron is in the middle, and then your heme or your porphyrin has 4 nitrogen. So you have 4 nitrogen right there, okay? And they will capture your iron in a plane, okay, so on the horizontal axis. Now, on the vertical axis, you still have to have things, right? Now, on the vertical axis, you have 2 things that can bind to iron that way. And usually we call this an octahedral coordination because, in general, after having 6 ligand on this metal ion, then what you have is essentially 8 sides, right? So that's why it's called octahedral. The iron and the 4 nitrogen from the porphyrin are nearly in a plane. Okay, it's not exactly in a plane, but close to a plane. Okay, now that is only the case when you have an oxygen bound to the iron. Okay, we'll see that today. Now, important for both hemoglobin and myoglobin is that here you have to have two histidines that are associated in this O2 capturing mechanism. And one of those histidine, we call that the proximal histidine. And this one directly interacts with the iron. Because remember that histidine, this atom right here, is a nitrogen. So it can directly interact with the iron. Now, on the other side, this is the place where you can bind molecular oxygen. Okay? What's the other histidine doing? Okay, so this other histidine has actually two functions. The first function is that it facilitates the binding of molecular oxygen by stabilizing it. Okay, so if you have molecular oxygen, so this guy is, this is O2 right here. So molecular oxygen comes in, and molecular oxygen will be attached to the iron atom. And then here, you also have the other histidine that is used to sort of interact with molecular oxygen and then stabilize it so that your heme can capture this O2. Now, two things. The histidine that binds to the iron, we call that proximal histidine. And the other one, we call that distal histidine. We're going to be referring to these two names in today's discussion, so let's get that straight. So, proximal histidine is the one that is linked to iron from the bottom. So, this guy, if you look at the picture on the right here, this guy, this histidine is attached to the iron. Distal, meaning like distance, right? Like further away. The distal histidine is here that is going to interact with this guy's O2, with oxygen. And then oxygen interacts with the heme. Here, just want to show you here that the distal histidine that we're using to interact with the molecular oxygen here, in particular, we're more interested in the epsilon tautomer. Here, why we mention this is because this particular H could be here, and then double bond could be here. Okay, if you make that into a single bond. So histidine itself, it's always a tautomer between the delta tautomer and the epsilon tautomer. But here in this discussion, we're primarily concerned with the epsilon tautomer because that's the position which will get close to the molecular oxygen to interact with the molecular oxygen. Here it says that the coordination of iron 2 in a porphyrin or heme within a hydrophobic globule pocket allows reversible O2 binding without iron oxidation. So in heme or in hemoglobin, myoglobin, the iron inside the heme has to be 2+, because if it's 3+, then it will not bind oxygen. Okay, so it won't. Now, if by accident or somehow your iron 2+ is oxidized to 3+, then this myoglobin, we all call them metmyoglobin. Okay, so it's not a functional myoglobin for O2 capture. But that's just a little term right there. The hydrogen bond between your distal histidine and molecular oxygen selectively increase the affinity of myoglobin for oxygen versus other things like carbon monoxide or NO, that kind of stuff. So let's say this is the heme, this is the iron, here is the proximal histidine, and molecular oxygen will actually be like that. Okay, so your histidine will actually be sort of on the side. Okay, so this guy can interact with molecular oxygen. Okay, now, if you have carbon monoxide is straight, so your proximal histidine does not really interact with carbon monoxide. The shape of the molecule is different. Okay, now. However, here it says that the distal histidine selectively increase the affinity for oxygen, right? However, turns out carbon monoxide still binds significantly more stronger than molecular oxygen. Even so, even with the distal histidine, your carbon monoxide still binds about 200 times more tightly to myoglobin than molecular oxygen does. Now, however, if you don't have distal histidine, then the ratio becomes 6,000 to 1. So you go from 200 to 1 to 6,000 to 1. Okay, so having the distal histidine there increase the affinity of your hemoglobin to O2 by a factor of, let's say, 30. Right? Because having that histidine there really stabilizes O2. Even though it doesn't stabilize carbon monoxide, but carbon monoxide is still very, very favorable for this binding. Why is that? Because this thing's essentially linear. Okay, so then you have a nicer coordination. So a little something here shows you why is it that your blood changes color between the oxygenated form and the deoxygenated form. Okay, so you know that in your arteries, the blood there is primarily red because it's oxygenated. Those blood essentially just took oxygen from your lungs and they're trying to go somewhere. So they're very oxygenated. And they're red. So arterial red. After they go through your body and stuff like that, and then when your blood is returning, they return via your veins, right? Okay. These are going to be a different color. You know that your veins, they don't look red, they look purple. So why is that? Turns out, whether or not you have this molecular oxygen here, it changes the location of the iron. So if your O2, this is O2, if O2 is present, okay, so if O2 is there, then your iron is going to be sort of in the middle of the heme. Okay, so that, of course, will have a electronic structure. Now, if O2 is gone, okay, so between this guy to this guy, you spit out O2, then now you don't have no O2 here. You don't have the molecular oxygen there. As a result, your proximal histidine will pull the iron down towards it. So now what you can see is that your iron is out of the plane. And in reality, what this will do to the heme is that it's going to cause the heme to be slightly tilted. So the heme is no longer in a plane. So then that disrupts your electronic structure. As a result, you get a different color. And that actually gives you a very good tool to measure the oxygen binding of this particular protein. Because what you can do is you can take this protein and then measure it using UV visible spectrophotometer, and then you can look at the color as a function of different oxygen amounts. Okay, so with increasing oxygen, go up. With decreasing oxygen, obviously you see how these two peaks will go down and then the middle peak will come up. So this is how iron is coordinated in oxymyoglobin. Oxymyoglobin just means that it has oxygen. Deoxymyoglobin just means that it doesn't have oxygen. Should be very straightforward. Inside of this particular pocket, inside of this hemoglobin or myoglobin pocket, in this pocket, it's hydrophobic. Why is that? Because having this in hydrophobic, it prevents molecular oxygen from coming in and oxidize your iron, or excessive amount of oxidizer. Okay, it prevents excessive amounts of oxidizer coming in and oxidize your iron. Now, here we're going to talk about how O2 is released. So once it binds, and how is it released? What you see is that there's dynamic motions of myoglobin, which facilitates ligand binding and release. And here by ligand, essentially it's talking about molecular oxygen. Now, the distal histidine, like I said, it has two functions, right? Number one function is it stabilizes the molecular oxygen binding. The other function is that it serves as sort of a door, a gate between the bounded O2 and the environment. Okay, so what does that mean? So as you can see, Here is your heme. Here is the proximal histidine down on the bottom. And this is the place where your O2 will bind. And then this here is your distal histidine. Okay? And what this sort of shows you is that the histidine can move like that. It moves. And then it sort of prevents your O2 from leaving, and it's sort of just like a gateway for the molecular oxygen to like move out. So your O2 will sort of move around inside the cage, leaving only a small percentage of the time. So essentially your O2 is going to be like, whoa, like that. And then sometimes when the histidine is, door opens and then this guy flies out. Make sense? Okay. Now, myoglobin has evolved to bind and release O2 under conditions of relatively low oxygen concentration. Okay, so it means that it has a good ability to bind oxygen. So this chart you'll see repeatedly, or this graph rather. This is an oxygen binding curve. Okay, and this is an oxygen binding curve for myoglobin, and you'll see a different one for hemoglobin as well. Okay, now let's first take a look. Here on the y-axis, this YO2 business, that's sort of the myoglobin binding sites that are occupied and expressed in a fraction. Okay, so total available binding site will be 1. So if all of the O2 binding site has oxygen on it, then you are going to be at 1. If you have no oxygen on it, then you're going to be at 0. So it's sort of like a 0% to a 100% bound. On the x-axis, you have partial pressure of oxygen. So this is the partial pressure of oxygen, and that is sort of used as an indicator for free oxygen concentration. Okay, because oxygen is it's a gas, so you can't really measure like the molarity of oxygen. So we usually just measure it or express it as the partial pressure of oxygen. Okay, so this guy's partial pressure of oxygen. So it sort of just says how much oxygen you have. Now, this is the oxygen binding curve. So as the partial pressure of oxygen becomes really large, then 100% saturation is approached asymptotically. So it sort of reaches an asymptote, and it never really reach 100% until you have like infinite large of concentration of oxygen. Here I want to highlight something special called P50. So in biology, we really like to use this thing blah blah 50. What P50 says is the partial pressure necessary to have 50% of saturation. Cross out the black arrow. I don't think this is black. It's indicated on the graph. So when you reach about half saturated at this particular concentration, we just call that P50. This is important, okay? You will repeatedly see a lot of this type of characterization for enzymes and proteins, okay? We always just said, 50% of the output, how much is the input, okay? How much of the input you need to give in order to get 50% of the output. So this is what it means. Now, what you see here is that here it says the dashed blue lines shows that at partial pressure of 30 millimolar mercury, right here, myoglobin would be 90% saturated with O2. And this 30 is about the partial pressure of oxygen inside of tissues. Okay, so in most of your tissues, your myoglobin will be able to capture a large amount of oxygen, so that your tissue will have oxygen to use. That's what it means, okay? Because at low level of molecular oxygen partial pressure, your protein is still able to bind O2. Okay, that's good, because as you use up the partial pressure here, then you can release the oxygen. Now, the reason why I want you guys to focus on P50 is that the P50 is an indicator of the relative binding affinity for globin for a particular ligand. Okay, so in this case, for globin with higher O2 binding affinity, then P50 is low. With a globin with lower O2 binding affinity, then P50 is high. It's a little counterintuitive because of the higher and lower, but essentially, hear me out. So lower the P50 means that you only need a little bit amount of your oxygen to reach 50% saturation. That means that your protein has a super good affinity for molecular oxygen. So let's get some expression out of this. In this process, essentially you have myoglobin plus O2, and it becomes bound myoglobin plus O2. And in this case, you have a rate constant for K on and K off. Right? Now, here we have the dissociation constant, okay, Kd, that's what the D stands for, which is generally speaking reactants over products. Okay? So this is sort of the unbound over bound. And we also define that the fraction of O2 bound on your protein is defined by sites occupied divided by total sites available. Make sense? Okay, so it's going to be a fraction. So what that means is sites occupied is essentially O2 bound on myoglobin, total sites available. You add up all the terms that have myoglobin. Okay, that's the total sites available. And the ones that are bound is essentially this. And then we know from dissociation constant that Kd is equal to Mb times O2 divided by MbO2. So you solve for the bound myoglobin and oxygen, and you do a little rearranging, and then this is the expression that you get. Simplify this expression because you can cross out the myoglobin concentrations. Then what you have is molecular oxygen divided by Kd over molecular oxygen divided by Kd plus 1. And then we can simplify that as essentially molecular oxygen divided by the dissociation constant plus molecular oxygen. And after having this particular equation, I know that Kd is nothing more than P50. How do I know? Because what you can do is you can set molecular oxygen concentration equal to Kd. Then what you have is Kd, so Kd, blah, blah, blah. And then it's going to equal to Kd over 2Kd is equal to 1/2. Okay, so this is YO2. So essentially it tells you that Kd, or the dissociation constant, is essentially the concentration needed to give you 50% of saturation. So if you plot this curve using a graphing calculator, you'll get a hyperbolic curve that looks just like that. So again, this is really, you just have to memorize this. A globin with high O2 affinity will have a low P50. Okay, globin with low O2 binding affinity will have a high P50, and it makes sense. So that's myoglobin, right? So that's how myoglobin works now. So now we're going to get into hemoglobin. Now, if you think about it, you have to be able to breathe molecular oxygen. Okay, so in atmosphere, there's 20% of oxygen there. You breathe oxygen, and then somehow you have to get oxygen to the different parts of your body. Okay, and we mentioned that in our previous class that animals are going to use hemoglobin to do this transport. So higher animals will use O2 binding protein to transport oxygen from lungs or gills, if you're a fish, to respiring tissues, okay, where it is needed to support metabolism. So we'll have to go from lungs to tissues. Now, what that means is the O2 binding affinity for hemoglobin should be weaker than myoglobin. Why is that? Because myoglobin are the O2 carrier inside of your tissue. So if hemoglobin has a stronger affinity, then what the hemoglobin will do is take away oxygen from your tissue. That doesn't make sense, right? So hemoglobin has to have a lower affinity compared to myoglobin, okay? Because otherwise, it's going to go reverse. Okay? So for hemoglobin has a lower affinity so that when hemoglobin travels to the tissue, it can pass the oxygen to myoglobin. So hemoglobin and many other O2 binding or transferring proteins are usually multi-subunit proteins. And multi-subunits basically means quaternary structure allow the protein to have cooperativity. Okay, we'll talk about cooperativity today. So obviously you see how between the different organisms you can have different large multi-subunit proteins that sort of interacts with molecular oxygen. Now, here we have two possible scenarios. So we say hemoglobin has to bind oxygen lower than myoglobin. Okay, so on the top line here, this guy, okay, so that's myoglobin. Okay, so the top, this is myoglobin. Okay, so the bottom one, you're going to call it transport protein. And you can have two types. You can have a strong binding transport protein or a weak binding transport protein. So let's take a look. In the strong binding one, even though it's still weaker than your myoglobin, but you see how the shapes sort of look pretty similar. So then essentially what you look at is the partial pressure in the lungs is about 100. Partial pressure in the tissue is about 30. We want to use this difference in partial pressure of oxygen to carry the oxygen from the lung to the tissue. Okay, so if we look at this strong binding transport protein at 100 PO2, you get about maybe 0.92 saturated, okay, 92% saturated. And then when this protein travels to the tissue, so at this position, this is the place where transport protein passes O2 to myoglobin. That's where it passes the O2. And how do I know that it will pass O2 to myoglobin? Because myoglobin binds at a stronger affinity than my transport protein. Now, this delta fraction, that is the fraction that is transferred from the hypothetical hemoglobin, the transport protein, to myoglobin. So that's the amount that you can transport. Now, if you look at this and you say, that sucks. Okay, why? Because look at how small this number is. You get about maybe 0.1 or maybe 0.15, something like that. Okay, I made up that number. So it's a small window. So that means that the loading, the unloading, the delivery person is not very efficient. Okay, so it says here that transport protein efficient in binding, but inefficient in unloading. So it's like a mailman who's like super good at taking mails from the post office, but sucks at delivering it. Okay, so not ideal, right? Because it doesn't like to give mails to people. Okay, so that's not good. So we look on the other side here. You have weak O2 binding, strong, not good. How about weak? Okay, so then this is very weak. And if it's weak, then it doesn't really bind O2 at all. So that at the lung, you got about 0.65. And then when it travels to the tissue, you got about 0.4. What's the problem here? Yes, okay, you can have a large gap between myoglobin and your transport protein. However, this transport protein sucks at picking up its package. It's horrible at loading. Okay? Even though it's going to be quite efficient in unloading, but the loading is also bad. Okay? So it's bad in both cases. In this case, then this guy is also not going to be an ideal protein, right? Because that means that for every transport protein that goes to your lung, it's only going to capture about 70% of its ability instead of capturing 100% of its ability. Right? So that means that it's kind of stupid. So these curves actually have a set affinity for O2. That means that if you have a set affinity for O2, you will never get to a middle ground. Okay? You will never get to an ideal situation. You have to be able to change the affinity depending on the location you're at. Okay? So neither high nor low is ideal for O2 delivery from lung to tissue. It would be better if you have high binding at lung, low binding at tissue. And then you're just like, yeah, that's, okay. Okay? All right? So it would be good to have that.